and running through today's agenda. So we'll start out with a quick background on model optimization, walking through advantages and disadvantages of it, state-of-the-art algorithms and techniques, how to apply these optimizations to a model, and available tools that are out there in the industry. Then we'll dive into an NLP text classification example, walking through how to optimize a BERT model specifically, and how that can be extended out to other models as well. So example integration and what we call recipes, and we'll get into recipes a little bit later. Additionally, we'll walk through after that, a computer vision object detection example, a YOLO v5 example. We'll walk through how to integrate and how to create a recipe to be able to optimize these models. And then finally, we'll conclude with next steps and discussion and open it up for a discussion. So to get everybody kind of engaged a little bit, we'd love to do a quick poll. Sasha's going to run this and kick it off. Big question is, have you optimized or sparsified a model in the past? So you should see it live now through Zoom. Feel free to go ahead and answer that question. And then we can, well, we'll give it a few minutes, we'll give it a minute or two, and then Sasha will present some of the info that we got. And don't worry, we'll walk through, in case you're not familiar with the terms, we'll walk through quantization and pruning in the intro.
All right, let's do 5 more seconds. I can't believe how 77% of people already responded, 78. All right, 5. It's still coming in, I lied. Let's do 5 more. 83% of people, 82. All right, I am going to end the poll now, and I think you guys should be able to see the results. I'm going to share those. Can you see them, Mark?
Yeah, perfect.
Right. I'll let you take it from here.
Yeah, sounds good. So it looks like we have 61% people that have not optimized the model, 20% that have quantized, 27% that have pruned, and 5% on other. Actually, really interesting. This is one of the first times we've had pruning higher than quantization. So so very interesting. But thank you guys for filling that out. And so diving in, let's go and talk over advantages and disadvantages of optimizing your model. So one advantage is that we can get significant speedups, and we'll go through speedups as we're going through this workshop and what can happen there. But additionally, we get model compression on top of that. So we have both inference speedups whenever we're looking at deploying the model, and additionally on inference, we can get model compression, so we can minimize the size of those files, so we can deploy them at edge and deploy them in more constrained spaces. So instead of taking up hundreds of megabytes of space, we can go down to a few megabytes or tens of megabytes. And then finally, we also, because of the significant speedups and the model compression, we additionally save on energy. And this has environmental concerns as well, trying to reduce the impact of deploying these models in production. Some of the disadvantages. So one part is it's not trivial to be able to optimize these models. It adds additional hyperparameters on top of it that they have to go through and fine tune. We'll talk over what we're doing at Neural Magic to make that easier. Additionally, it's adding another step into your process. So this doesn't mean that you'll have to go through, in best case, a new evaluation on your validation data set to make sure that the model has not changed and has not shifted significantly. The second, and at the extreme, you might have to retrain the model. So it is another step that adds on to your current training flows. And then finally, there's a lot of kind of in the space that model optimizations are going to drop accuracy, and to signify the significant speedups that we get, and also to speak towards the dropping of accuracy. Here's some results that we have for a ResNet 50 model. So an image classification model, what we're able to do to optimize this model, these all get within 99% of the accuracy of our baseline gray here. But you can see that we can go all the way from 315 items per second to, once we prune and quantize the model, all the way up to 2,500, right? So a significant improvement in that performance that makes it much cheaper to deploy, much faster to deploy, and takes less energy as we're running. And let's go ahead and run through some state-of-the-art algorithms and techniques. So one is looking at unstructured / semi-structured pruning. So as we can see on the right over here, we have a fully connected network. And what we're going to do is remove the individual weight connections in between our nodes. Right, so we end up with a not so fully connected network on the right. So the big thing here is that we're removing these individual weights by masking them to 0, and we're keeping the matrix shapes. And then going through the algorithms a little bit, there's magnitude pruning, which just looks at how far away each weight is from 0, and prunes the ones that are closest. We have movement pruning, which is a first order technique, which combines gradient information with the weights and prunes the ones that are actually moving towards 0. And then we have Wood-Fisher, which actually came out of collaboration with Neural Magic and IST Austria with our research scientist, Dan Alistar, which looks at second order information. So it's actually calculating how much each weight affects the loss function and then pruning away the ones that affect it the least. And then we have structured pruning. So this is where we're removing large sections of the weights by actually changing the tensor shape. So instead of masking with zeros, we're going to come in and remove channels, for example, for this fully connected network. So we remove 3 of the channels in that middle layer, right? And that's removing whole groups of these weight connections at a time. And that does end up changing the tensor shape. There are other techniques outside of channel. There's also filter for convolutional neural networks, layer pruning, which can happen where we just remove whole layers. So like in ResNets, we can remove a whole convolutional layer, and transformers, we can remove a whole transformer layer. And then specific to transformers, we also have attention head pruning, where we can remove individual attention heads within it to try and get speed up. And after that, we also have quantization. So quantization is where we're reducing the precision of the activations and weights. So if we look at the nodes and the weight connections here, what we're actually doing is taking, usually these are represented in FP32. We can reduce these down to int8, for example. So make these much smaller so that the data movement is much less, and the compute, and we get compute speed up from that. Looking at int8 versus less than int8. int8 generally works across the board. There is support for less than int8, so being down to like int4, int2, binary networks, things like that. There isn't a lot of support for hardware speedup for those networks currently. So at Neural Magic, we're primarily focused on int8. And additionally, we have this concept of dynamic versus static. And we'll get into this a little bit actually on the next slide, walking through what that means for application. But dynamic is where we look at, as the activations are flowing through the network, we're going to calculate a distribution across those activations so we can actually convert them into an int8 format, right? So we get the max and the min as the activations are flowing through, and then we can take it from an FP32 representation down into an int8 distribution. Static is going to run a bunch of samples through the model, and this can be done either post-training or while we're training, but we're going to run a bunch of samples through the network, and we're going to calculate a distribution for those, so that we're not actively calculating this as we're running the network. And then finally, we have distillation. So distillation is where we're going to distill information from a larger teacher into a student model, right? So if we have a larger teacher that's more accurate, we want our student model to try and match the outputs from the teacher as close as possible to ultimately make the student more accurate. And there's a few different types of distillation, including response, feature, and relation. I won't go into too much detail. We will have docs up on these to dive into these more. But at a high level, response is just looking at the outputs from the teacher and the student, making sure that they match. Feature is where we actually match in between layers. So BERT, it has 12 layers. We can actually match the outputs at every single layer from a larger teacher. And this usually gets us a little bit better accuracy. We also have relation, where we can start looking at mass within like an attention head and things like that to try and map the exact algorithm that's happening internally to those weights, rather than just mapping the activations. And so let's walk through what it looks like to actually apply those optimizations to a model. So we have post-training, or sometimes referred to as one-shot. This is applied after training using the model and the sample data. So you can see we have faded out the old model, and then what we can do is use some sample data and quantize and prune and end up with a much smaller version than we originally had without retraining. It works well for dynamic quantization, but it currently doesn't work well for pruning. We drop a lot of accuracy if we try and do it for pruning. But we do actually have some new research that is currently going through a review process, and we're looking to actively productize that as well. So stay tuned for that, and definitely follow us to stay in the loop. And then after that, we have training aware. So this is where optimizations are applied during training. So for example, instead of pruning a model and not retraining, what we can do is actually prune step by step. So prune at 10%, retrain for a little bit, prune at 20%, retrain for a little bit, where we're removing 20% of the weights, and continue training. What this allows us to do is converge to a solution, to an accurate solution much easier. It works well for both pruning and quantization. And finally, we have sparse transfer. So this is where we're going to fine-tune a pre-sparsified model onto a new data set. So for example, we can take a pre-trained BERT or a pre-trained ResNet 50 that have been sparsified on larger data sets. So BERT, like on top of the Wikipedia data set, for ResNet on top of the ImageNet data set. And what that creates is a general sparse architecture that can now be fine-tuned onto whatever data set you'd like. Oh. And one other thing to say about that is just sparse transfer is generally easier. We don't have to worry about hyperparameter tuning or anything like that, like we do for post-training and training aware, because the sparse architecture already exists. So this is generally easier to do. And then let's walk through some available tools. So first is there are some algorithms built into PyTorch and TensorFlow. It has pretty limited support, generally just basic pruning, magnitude pruning, and then basic quantization support for both dynamic and static. And to be able to implement these, the optimizations are actually all defined in code. So to be able to implement for a new model, you have to have the model definition. You have to completely rewrite the code that you're working on for each model. So not extremely scalable. We can look at NVIDIA Transfer Learning Toolkit, TensorRT, and TensorRT, as well as Intel and NCF. So it has, generally both these tools have good one-shot support, but they have limited integration and training capabilities. They don't hook into training pipelines super well. And this is an issue, especially for pruning, where we do want to do this training aware pruning to be able to work, and also for quantization just to get better recovery. And then additionally, you have research libraries. So for these research libraries, there's generally good single algorithm support for these. So for example, pretty much any of the new pruning research that's coming out or quantization research that's coming out, it'll get open source, but only implemented for that specific algorithm and only implemented for the specific models that were released with the research paper. So there's limited integration and limited multi-model support. And then finally, we have some UIs like Accompanying and DESI. So these wrap a lot of the above tools with some additional algorithm development on top of it. And generally, they only support one shot to be able to work with. So really limited in pruning and quantization in terms of being able to get full recovery and get to that 99% threshold to make sure that we're not affecting whatever model that you're putting into production. And additionally, they're hidden behind a paywall. So, they can be harder to use and harder to get access to. So let's walk through neural magic tools now. So generally what we're doing is building an optimization platform around recipes. And recipes are defined in YAML. So meaning that we have all of our optimizations, whether it's pruning or quantization, and this is what we'll be going through for the workshop. We have all these defined in YAML and not code. And this means that we can integrate into, whether it's YOLO or Hugging Face or any of these training and deployment pipelines, we can integrate into these once, and then you can configure just through YAML, through a readable YAML script, and not have to worry about changing the code anymore, right? So it becomes much more pluggable, and you can create versions of it rather than having to implement for every single model within the code. So we have SparseZoo, which is where we keep state-of-the-art recipes for optimizing models. So our internal research is what we're going to be pushing up for those recipes, and the results of those recipes, which are pre-optimized models that you can use for sparse transfer learning. Additionally, we are actually actively working hard right now on enabling community contributions. So again, stay tuned for that, and definitely follow us as we release that. Then we have SparseML. So it has support for many state-of-the-art algorithms and integrations, and it's only a few lines of code required to actually apply a recipe. So to take a model and then go into optimization through your training pipelines, it's only a few lines of code, or even one shot, it's only a few lines of code to actually apply, and we're just loading that recipe and being able to apply on top of it. The recipes contain what we call modifiers, which are going to modify any training graph so that we can do quantization, we can do pruning. We can even modify learning rate, as we'll see later, and things like that. And finally, SparseML is open source and growing. So if you're interested in contributing, definitely stop by our GitHub repo and check it out. And so we're going to jump into NLP use cases next. But before we do, we're really interested in just seeing what NLP use cases you might be using for production now, if any. So Sasha's going to go ahead and kick off that poll.
Is it launched? Oh, there it is.
Yep, there we go. Perfect. All right, so just a few, a few different use cases. Obviously, it's not quite a few in there, but definitely not exhaustive. So we'd love to hear what you guys are working on.
We didn't see any results coming. I didn't see any results coming in right away, and I got nervous. But then I understood that it takes a second to go through all the options, obviously. We have about 48% of people responded already. Let's give it another 20 seconds. And thank you everyone for really engaging with these polls. It gives us an idea of what you're working on, so we can really tailor this, in future discussions. That. All right, 63% of people. I'm going to end there right now and share the results.
All right, awesome. So looks like the most popular was text classification. Definitely matches with a lot of what we've seen internally, and quite a bit for document classification, which is a pipeline that we're actually working on right now, actually to show examples for. Yeah, all really, really good information. And we'll go through a little bit and at the end on future work that actually aligns with quite a bit of this as well. So thank you everyone for filling that out.
And I see that 21% of people said other. It would be cool. You don't have to, but it would be cool if you want to drop it in chat or the Q&A feature and let us know what you're working on. Back to you, Mark.
Yeah, definitely. So let's go ahead and look at an NLP integration performance. I know there are quite a few questions coming through, so we can hopefully alleviate some of those. So for NLP integration, we're integrated with Hugging Face transformers for SparseML and SparseZoo. So SparseML being a Python-based optimization framework, and we're integrated with the Python-based Hugging Face transformers, specifically on their PyTorch pathway. So what you can do is pip install SparseML with our saying that you want to use the PyTorch version. And then immediately what that's going to do is install a command line interface that's available. And you can just use sparseml.transformers.text classification, for example. We also have question answering and token classification and a few others. So you can check those out and use the help function just to immediately begin using those. The critical thing being that our integrations now accept recipes to be able to optimize these models. So we have BERT models and recipes available on the SparseZoo. We'll go through those in a second as we get out of the presentation mode. But additionally, we have BERT large and distill BERT coming up. And finally, you can do your own custom integration through Hugging Face as well. So we have just a general trainer class in case you don't want to use our active CLIs. You can use our general trainer class and plug it into whatever pipelines you might be using, including custom tokenizers and things like that. And then to go through a little bit on performance of what we see for BERT. So for example, going across BERT large, BERT base, and distill BERT, you can see that we get significant speedups to the point that BERT large actually beats distill BERT, the distill BERT base once we sparsify and quantize it. So this is going to get to 80% sparse. So we're moving 80% of the weights across the networks. This is for BERT large, BERT base, and distill BERT. All of them are 80%. You can see significant speedups over the top of what our baseline was. Yeah, so these are all throughput results. Let's go ahead and dive into how we actually go about doing that and creating these. So let's talk over creating an NLP recipe. We'll start with quantization aware training, and we have a few modifiers that make that up. That we'll talk over how to create a recipe with and actually show how to go about that process. So we have an epoch range modifier, which is just going to control how long we train for. We have a learning rate function modifier, which is going to control our learning rate so that we can adjust it for quantization. Then we have a quantization modifier, which is actually going to go through and take the model and then apply quantization ops on top of it, edit it, so that we're no longer in FP32, we're actually running as a quantized model. So to start off with, one thing I just want to call out real fast is if you go to neuralmagic.com and scroll down a little bit, we do have all of these try it now features with example scripts that you can kick off and use. So you'll see the recipe argument right here, but you can kick these off and try them out without having to dive into the documentation too much. Diving into documentation though, all of this is stored, and we have the links in our presentation. All this is stored under SparseML in our open source. And this is where everything exists for transformers. So it's source, SparseML, transformers. And you can see that we have mass language modeling, question answering, text classification, token classification as our pipelines, as well as just general utilities to be able to implement this in your own pipelines. Diving into, for example, one of the readmes for text classification, this will walk you through how to go about installation, walk you through the arguments and things like that. So just looking at the CLI, you generally just want to give it a model, what your task is, or you can give it custom data as well. And then you can begin training. The rest of these are going to be training arcs. The final thing to call out is that for NLP, most of these are using distillation to be able to get really good recovery. And we'll go through what that looks like for a recipe after as well. And then the final thing to call out before we dive into recipes is just that all these are available on the SparseZoo. You can go through, we have a lot of BERT models pushed up if you'd like to explore. Clicking into one of these, you can see that, we do have all the recipe pushed up as well. So if you want to look at, and this is what we're going to start going through next now, you can look through what this looks like to take, for example, our sparse BERT version and then transfer it onto your own data set. So this is what a recipe actually looks like. We're going to go through each piece of this. But additionally, for those recipes, we have a quick README on how to use these and how to override arguments in case you want to try out different hyperparameters and things like that. All right, great. And the other thing I just wanted to call out real fast is how to just kind of showing off the CLI. So I've already installed SparseML. And as soon as it's installed, then we can just do that SparseML.transformers.text classification -- help. And this just makes it available. It's very close to the Hugging Face example scripts that they put out. We just added a little bit more support on top of it. And you can see it's going to print out a bunch of different arguments, a lot of Hugging Face arguments. Hugging Face has a lot of arguments built in, but you can see that this is just going to be your general pathway for training those. All right, so let's look at creating a quantized, what actually optimizing model set is just quantized looks like. So what we're going to do is start off with something saying modifiers. And we're going to start creating groups of modifiers under here. Generally, 5 epochs for BERT gets us to pretty good recovery for quantization aware training. So what we'll do is we'll say epoch range modifier, and we're going to train for 5 epochs. After that, what we want to do is set our learning rate. And this is where our learning rate function modifier comes in. So just diving into this, what we'll do is say that starting at epoch 0 and ending at epoch 5, we want to linearly scale from this learning rate to this learning rate. All these learning rates are pretty, if you're familiar with tuning BERT and other NLP models through transformers, these are going to be pretty close to the hyperparameters you would use there. But this is kind of the experience or the pieces that you have to go through and figure out for hyperparameters. And that's why we push up those pre-trained recipes so you can just use those off the shelf rather than having to come up with these on your own. And finally, what we'll do, and the kind of key piece to actually making this quantized, is using our quantized modifier. So we're going to tell it we want to use a quantization modifier starting at epoch 0. So immediately as soon as we start training, we're going to take over the graph and start it as quantized. These two are generally just PyTorch implementations, meaning that we're going to stop observing our activations and freeze bash norms and things like that towards the end of our quantization training. Generally for these, you'll just want to do 1 minus whatever your end epoch is. What we're going to tell it additionally is to ignore layer norm and 10H. So we don't want to try and quantize these. These don't really get speed up from quantization and can hurt accuracy. But what we do want to target are the embeddings in BERT. the encoder layers in BERT, so the attention and the fully connected, and then the end classifier in BERT. And that's where we get all the speed up from. So what we would do is we'd save the take this BERT underscore quant.yaml, and we would use the SparseML.transformers.text classification. I'm not going to run it right now because it would take a little bit of time. I'm sure everybody doesn't. Actually, let me clear this out real fast. I'm sure everybody doesn't want to sit here and watch a weights and biases graph for like 30 minutes. But we'll do SparseML.transformers.text classification. The key thing is going to be passing in that recipe, and additionally the model. So that's we BERT.yaml. So we just do BERT quant.yaml, and then additionally we do our model, which we can set to uncase, for example, and that's just going to pull down the Hugging Face BERT model and then begin the quantization flow on that. All right, great. And then looking at sparse transfer. So this is looking at those models that we have pushed up here, right? So we have a 80% pruned model that we can quantize and transfer to our data set. So this was pruned on the Wikipedia book corpus data sets so that it can generalize to whatever your NLP use case is and NLP data set. So we're going to look at what sparse transfer would look like for that. So again, what we're going to define is our modifiers and specifically how long we want to train for this. Oh, and I apologize because this file is not named correctly. I don't know why it got the Python extension on it, so sorry about that. Instead of trying to fix that now, we will just override our BERT quantized one. So we have modifiers, and we're going to train, in this case for 13 epochs, this is completely controllable by you. Generally 5 epochs for fine tuning at sparse, and then 5 epochs of additional quantization afterwards. Works pretty well for all of the different kind of glue tasks and other use cases that we were seeing, including squat and others. So what we'll do is, again, define our learning rate function modifier. And we're going to start at epoch 0 and end at epoch 13. And we're just going to go from this learning rate to this learning rate linearly. Additionally, we'll want to add in a distillation modifier. So whatever you've used to, if you're using BERT or anything like that, you usually have a dense model that you've already converged. We'll want to pass that into our script here. And what it's going to do is use the distillation modifier to be able to target that. So for our text classification example, we're going to target distillation on the logits, so the end output from the network. And whatever your teacher is coming in, your dense teacher, our sparse model is going to try and match those outputs as closely as possible. And this is how we get to really, really good recovery. This is how we get to that 99% recovery at 80% sparsity for block 4. And then final, well, almost done. One remaining piece is the constant pruning modifier. So what we want to do is say that given that we have the sparse architecture coming in, right, as 80% of the weights in there all zeroed out, we want to tell it to keep those weights zeroed out. So that's all that this modifier is going to do. Given that model coming in, we're going to keep those weights 0 and while we're training. So it's not going to update those weights at all. And then finally, after we've finished training and converge on our solution with the sparse architecture, then we'll add in our quantization modifier again, just like we were doing before. This time we're just going to start after we've converged, and then allow it to train for another 5 epochs to get the quantized version. Great. And then what this would look like is, given our command here, we have this, and then what we'll want to do is pass in our distill teacher, and we'll give it whatever the local path is to our distill teacher. So to our dense version of that model that we already have, we can do dense teacher and pass that in, and then we can kick that off. And what that's going to do is create a sparse quantized version for us that's ready to run and ready to deploy after. And then the final one that I want to run through with everyone is just how do we go about creating one of these recipes from scratch? So generally what we'll see, and these are write-ups that we're actually working on, tutorials that we're working on currently. We have a little bit pushed up in the SparseML now around the hyperparameters for it. We can do epoch range modifier. So we'll want to do 35 epochs. The one thing I want to call out is that you can actually use mathematical functions in here. So it's just going to evaluate the 35, but you could actually do ×2 or something like that. So this makes it a little bit easier to parameterize everything. So we have an epoch range modifier, and we're going to do our learning rate and distillation modifiers that we were talking about before, and put those in. And what this is going to do again is control our learning rate so that we have a smooth transition from our start to our finish, and then add in our distillation so that we can distill from our teacher model. After that, instead of using a constant pruning modifier, what we'll use is a magnitude pruning modifier. And what we're going to tell it is just target all of the prunable params and prune them starting at 50% at our start epoch at 0 in this case. Prune them from 50% and then prune them all the way to 90%. And we're going to update that pruning 10 times every epoch up until epoch 26. The mask type is something that's specific to VNNI. We do have documentation on this, so I'm not going to go into too much detail, but it's just specifically that VNNI requires a 4-block structure instead of a truly unstructured setup. And then finally, what we'll do is add in our quantization modifier. So after we've pruned the model and it's converged, then we're just going to end with quantization. Pruning, whenever we're pruning from scratch, it usually generally takes longer to run than the sparse transfer one will. But this gives you an example of what all of that would look like. All right, great. And then again, in case you don't want to go through creating these, or you just want to use something off the shelf, we have all of these pushed up to the SparseZoo, so you can just use these as is. And the neuralmagic.com website has some quick examples that you can run through. And additionally, it has some try it now resources that will actually walk you through, which I can't find. There they are. Use cases, natural language processing. These will actually walk you through the entire step of creating a teacher. Well, first benchmarking and then creating a teacher, which is down here. Create a teacher and then creating that transfer learning to that sparse model. And this is the easiest pathway to get started through our open source repositories. And then the final thing, so there's all of those. Final thing I want to call out is just if you're doing advanced. So one thing is we have the MFAC pruning modifier. And then additionally, if you want to try and target per layer instead of just saying you want to prune all of the layers. So going through those real fast. Under our sparsification pathway in our PyTorch, this contains all of our modifiers. So you can play around with them and look at them. And they're organized pretty well. So pruning, for example, we have something called MFAC. And this is that second order algorithm that I was talking about earlier that gets really good recovery. So you can see that all this is fully documented. It'll walk you through how to use it, all the parameters that you can use, and then some example modifier YAML that you can plug in to your recipes. And finally, for the advanced use case where we want to, let me pull up my Python console, sorry about that, where we want to try and get our own layers, right? So what we can do is use, well, first we're going to get our BERT model. So we're going to use this real fast. And this is going to create a sparse auto model. So what we're going to do is just create a BERT model really fast, and I'll show you guys, show everyone how we can go about actually figuring out which layers are prunable, which layers are quantizable. So if BERT, we'll do sparse auto model dot. Let's do text classification. Sorry, I believe it's dashes. So we'll create a BERT model really fast. Okay, and now what we can do is use some utilities that we have in SparseML to figure out which layers are prunable actually in that BERT model and which ones are quantizable. So we've imported those. And for example, we can now print out all of the quantizable layers that are available in that BERT model. So you can go through and see and pick which ones you might want to use. So for example, whenever we're looking at the encoder, we just targeted BERT.encoder, which is going to quantize everything else underneath that. And we can do the same for pruning. So we can use get prunable layers, and that'll print out all of our prunable layers. And before we were, again, just targeting all of the printable ones, which is going to look at all the attention matrices and the fully connected, like the query key value and the dense fully connected. All right, great. So let's go ahead and move on to another quick poll, because we're going to go into our object detection use case next. So before we dive into that, love to see if anybody on this workshop is using any computer vision use cases. So Sasha's going to kick off that poll real fast. All right, perfect. So as you can see, we have a few under there. Love to see what you guys are working on. We do have support for object detection, image classification, image segmentation right now, and looking to see which other ones we might want to build out.
Okay, we'll do a few more seconds. We have 53% of people, of attendees, I should say. All right, I'll end the poll now at 56%. Sharing the results.
All right, great. Wow, so it looks like a lot of people doing object detection. So that's great. I will be going through that use case next. So 70% using object detection, about 50% using image classification, and quite a bit using image segmentation as well. And Sasha, to your point, 19% on other. So anybody, if you're using others, feel free to chat them out or reach out to us separately. All right, great. So let's look through what our integration and performance looks like for object detection. So we integrated SparseML and SparseZoo with the Ultralytics YOLO v5 repo. So again, this is Python based, working in PyTorch as the framework. So you can do pip install SparseML torch. And what this is going to do is make SparseML.objectDetection.train, for example, and a few other arguments available. So you can begin training object detection models. This is specifically for YOLO v5. We have YOLO v5 models and recipes available and pushed up to the SparseZoo. So we'll show those in a little bit. And we're actually working on the new YOLO v6, v5, v6 models. Nomenclature is a little confusing on those right now, but technically the new v6 models. We're working on those and hope to have those pushed up soon. And then, let me go back one. Additionally, you can go through custom integrations if you'd like through SparseML. So actually on the SparseML README, we walk through how to go through a custom integration at kind of a YOLO v5 level or others. What you'll do is you'll import something called the scheduled modifier manager. What this is going to do is be able to turn the recipe into the actual modifiers. And then what we do is wrap, at least for PyTorch, what we do is wrap the optimizer. So you can do manager.modify. This is going to wrap the optimizer so we can take over, as we said, in only a few lines of code, we can take over the training graph and apply all of these optimizations, regardless of the model or the complexity of the training platform. Let's look at performance real fast. So we have YOLO v5L and YOLO v5S, for example. You can see that in this case, they're a little bit less than 80%, but for the YOLO v5L, YOLO v5S actually is around 70% sparsity. You can see for the YOLO v5L, we get to 130.2 items per second for the sparse and quantized version, which beats the YOLO v5S baseline, right? So much more accurate model. We can actually compress down to keep most of the accuracy for that model, but make it run as fast as a much smaller model. And as you can see for YOLO v5S, we can significantly increase the speed of that one as well. So this was looking at throughput at an image size of 640 by 640 and a batch size of 64 for that throughput use case. All right, so let's go ahead and dive into, well, actually, before I dive into creating the recipes, let's go ahead and go through a few of those resources. So everything's available, under SparseML PyTorch object detection under our source code. We are actively pushing up READMEs and things like that on those currently. So stay tuned for that so we can make those easier to use. But additionally, all the models are pushed up to the SparseZoo. So we have YOLO v5s, YOLO v5l, for example, and looking at one of these, YOLO v5s, you can take this and you can look at both the original recipe that created it, so you can use those if you'd like, as well as instructions on how to use it, in addition to a transfer learning recipe. So here's all of our arguments that we'll go through in a second. And then additionally, the README to walk through how to use it. All right, so let's walk through what it looks like for quantization aware training. One difference is that we're going to use over NLPs that we're going to use the set learning rate modifier in this case. This is specifically because we found, at least for computer vision side, that keeping a stable small learning rate works better compared to NLP, where we want to have a linear learning rate that's scaling. So let's look through what that looks like to actually create a recipe here. All right, and we'll come back to the command in a second. All right, so we can do YOLO quantize. And what we'll do is the same thing that we were doing before for NLP. We'll start with modifiers and we'll tell it how long to train for. So we can put an end epoch of 2. This is only going to train for 2 epochs. Quantization is pretty fast for the CV models, computer vision models. And then what we'll do is set our learning rate that we want to use for quantization. Again, a really small learning rate works very well. You can kind of think of it as we don't want to disturb whatever local min we're at after we've converged this model. So we use a really small learning rate in comparison to what it was trained at. And this allows us to essentially just adjust the weights so that they work with quantization rather than trying to retrain them to a new local min. And then finally, we can do the quantization modifier. So this one's a little bit longer. You can see that we have a bunch of model.0, model.1, model.2. This is a specific for the YOLO models, which is that if we were to target model at the root, we'd include the NMS at the end, which we don't actually want to quantize that. So what we do is we just list out the model.numbers that we want to target for quantization. Additionally, we avoid trying to quantize the end heads on the network just to save a little bit of accuracy. So that's all that this is doing in targeting. Again, you can use the get quantizable layers and the get prunable param. Well, get prunable params for later. You use get quantizable layers to figure out which ones you should actually be targeting. And then looking at this use case, let me get rid of this old command that we're walking through. So in this case, we can do SparseML. If my cursor will go faster, there we go. SparseML.object detection.train. And let me just print that out real fast. So you can see the help pathway. And again, this is just overriding the Ultralytics YOLO v5 pathway, and we're adding in our recipe arguments on top of it. So these are all the standard YOLO v5 Ultralytics training pathways, and we're just going to pass in our recipe argument on top of that. So what this would look like then is we'd have a config for the model for YOLO v5s, for example, or YOLO v5l. The recipe that we created there because of the quantized submodules that's targeting YOLO v5s. What we can do is add in a recipe here, and we called it YOLO_quant.yaml. And we can use that as our, and then we can kick off this training command with the model config. Again, we have all of this in our open source if you'd like, and on the recipes if you'd like to look at the full commands and be able to replicate and use it on your own data. And then we'll go through sparse transfer really quickly and pruning from scratch really quickly because we're running a little bit short on time. I want to keep a little bit of time for discussion, but I'm just going to paste all of this in here. So epoch range modifier for sparse transfer, generally we do about 52 epochs, 2 epochs of quantization on top of for converging the YOLO models on a data set. These learning rate modifiers here are just to mimic what was in the Ultralytics setup. So what you'll notice is that actually with learning rate function modifiers, we can actually target different param groups of the optimizer. So what we're targeting here are actually the weight groups, and then this is the bias groups. The Ultralytics setup warms them up differently in terms of learning rate. So this is just mimicking what Ultralytics does in-house for their configuration. And then finally, we'll just do a cosine learning rate, where we start at 0.032 and use a cosine function all the way down to 0.00384. Finally, we'll do our set learning rate for once quantization starts. But during all of that, we're going to use our constant pruning modifier. So we keep, again, the mass that were learned when we created that model and sparsified that original model on a COCO data set. We're going to keep those masks all at 0 so that we can do the sparse transfer. And then we'll add in our quantization that we had from earlier. All right. And then finally, we have pruning from scratch. So the pruning from scratch is going to look very similar to our sparse transfer, but with two kind of key changes. One is the length of time that we do it for. So generally for pruning the YOLO models, we train for about the same time that the original model was trained for. So we'll take the dense converged model, start off with that, and then apply this recipe on top of it. So we'll train for 302 epochs. 300 epochs of that is is working with pruning and convergence, and then 2 epochs at the end for quantization. So we have our same learning rate function modifiers and a set learning rate modifier for the quantization. And what we'll end with is global magnitude pruning modifier. So what this one is going to do in comparison to what we were doing on the NLP side is we're going to use this modifier to say globally across all the weights, rank all of those that so that we get to 80% sparsity as shown here. So the difference here between what we did with NLP is that NLP we're looking at every single parameter individually. We're making sure that every single parameter got to the 80% that it was targeting. Here, we could have some layers that are at 50%, some layers that are at 95%, because we're looking globally across the model. Essentially, you can think of it as combining all the params into one, and then re-ranking all of those so that we get rid of the smallest params globally across the model. And this works out very well for computer vision models, but not as well for NLP models. All right, great. And we went through all of this. So then let's talk through future work. So for us, we're looking at more models. We're looking at YOLO v6, VIT, UNet, Roberta, MiniLM, T5, GPT-2, and GPT-3. These are all models that are on our list that we've had interest for, and would love to hear from everyone what they're interested in using. Additionally, we have more use cases coming up. So big ones that we're targeting currently are information retrieval, and then looking at, on the NLP side, more generation tasks like summarization and translation. And then on the computer vision side, we're looking at segmentation. So we have YOLAC models currently and looking at UNet in addition. We're also working on adding in additional compression methods like better distillation. So currently we have just the end output distillation, and being able to add in better distillation like MiniLM uses and things like that. Additionally, adding more support for structured and further pruning improvements as new algorithms come out to be able to use those. And additionally, as I mentioned earlier, working hard on our one-shot implementations, especially making pruning feasible for one-shot. We have a lot of really good research coming out right now, and really working hard to get that productized and pushed out so everyone can use it. And then a big push for us is focusing on ease of use and automation. So we're working on a revamp of our docs right now to get them updated and simplified. And then additionally working on automated recipe creation. So all those recipes I was just going through, working on making it so that we can automate that process and then put a UI on top of it so that it's very easy to configure and tune. And then finally, feel free to get involved. We are actually actively working on a redesign of the SparseZoo website. We are looking for feedback from as many people as we can to make sure we get a good improvement on top of it. So feel free to go to this link, help us build SparseZoo, to be able to sign up and give us some feedback on the SparseZoo UI. And then closing remarks, to get started with your own data, as I mentioned, you can go to neuralmagic.com/use cases. Additionally, join our community going into, we have Slack, and you can also follow us on Twitter and LinkedIn. And then feel free to give us a star on GitHub if you think all of these tools are useful and would like to contribute or would like to use github.com/neuralmagic for everything. And follow us on Twitter @neuralmagic. So I think that's well, only one final call out. I forgot that we put this in here, Sasha. But yeah, we are actively hiring for a lot of different positions, including DevOps, ML engineering, high performance computing engineers, product engineering, a lot of stuff on marketing and product engineering as well. So if you're interested and like what we're working on, feel free to apply. Go to neuralmagic.com/careers to see the roles that we're looking for and see if it matches up with what you're looking for. So thank you everyone for signing in, and then definitely thank you to Michael. I've seen a lot of questions going by in my peripheral, so thank you for going through all of those. But we'll open it up now to discussion Q&A and see if there are any additional questions that are coming in.
Also, feel free to look through the questions I answered, as you can definitely answer some better than me.
Right, definitely. So let me go ahead and pull those up, and we can go through. So I think two that we have unanswered right now. One is there any other resources and materials to dig deeper in the topic? So if you'd like to find out more, feel free to go to docs.neuralmagic.com, as well as visiting our GitHub repo for SparseML and for Deep Sparse. All of those have a lot of additional tutorials and documentation within them, so that so you can get up and running on them. Additional question that came in: can we optimize custom-made TensorFlow models with custom-defined classes? This is an excellent question. We do have limited support for TensorFlow right now, specifically TensorFlow v1 for pruning, and then early Keras versions for pruning. Our primary focus has been on the PyTorch pathway. So it's not a preferred pathway for us right now, but if there's something specific that you're looking for getting support for, feel free to send it over to us, and we can see what we can do and see what we can do to get it into the product pipeline. Michael, I think you're best for this next one. I see you typing an answer in, but do you want to go ahead and give a live answer to it?
Yeah, I think PPC is a PowerPC computer architecture. Yeah, currently our engine targets x86, so Intel and AMD chips and instances, and we're working on support for ARM as well, CPUs.
Thanks, Michael. Let's see. Another one said, I subscribe to your channel. Hope you make more detailed video about object detection.train. Yeah, we're definitely working on a lot more documentation across all of this. And yeah, Sasha, maybe that's a good note. Maybe we can do some dedicated follow-ups on specifically the new tooling and NLP and object detection and things like that. All right, and then we have another one. Does int8 quantization include activations? Does it default to 8-bit, 16-bit, or 32-bit accumulation? And can I control the accumulation data type? That is a great question. So generally what will happen, I mean, dynamic or static, both of them are going to work to, at least the graphs that we create are going to work to try and keep the activations in int8 for as long as possible. This is how we get savings on data movement and also the size of the network. So we are looking at int8 for the activations, and then int8 for the weights. This is a great question though, which is that it is going to accumulate after we do the multiplications and the additions. It's going to accumulate into 32-bit. Generally what we'll do is then re-quantize that back down to int8 so that later layers can work with int8 and we're not getting hit with the movement of 32-bit. We currently don't have any control over the accumulation data type. It's something definitely to look into, especially as we start exploring lower bit precisions. But this is generally going to be on the engine implementation in terms of what it's going to accumulate into. And for 8-bit, it has to accumulate into 32-bit to avoid overflows. Another question, have you looked at streaming video-based optimizations for autonomous driving? A key application would be reducing latency to a fixed real-time constraint. So this is a really good question. We haven't worked specifically on autonomous driving, but it's definitely been a target for us, just in general for the object detection and segmentation models. A lot of this work that we're doing, pruning and quantization, works well, especially when we compare to on CPUs versus GPUs for the latency constraints. You can actually get really good performant late and low latency models on CPUs. so that we're not taxing the rest of the system. You don't need an expensive GPU in your car to be able to do self-driving. But yeah, if there's any more that you'd like to hear on that, feel free to reach out, and we can dive in more. Another question, can you speak on the steps to run on a purely custom model? So this is a great question. So if you go to the GitHub repo for SparseML, we'll walk through what it looks like to actually do the few lines of code to be able to enable your integration. Ultimately, what you'll need to do is make sure that our manager that is going to load the recipe can override the optimizer. It needs to have access to the model and to the optimizer. And what it's going to do is override the optimizer, and that's how we get access to the training graph. So that's what that would look like just in general in terms of the coding implementation, making sure that you can integrate it into the training pipeline. After that, you'd want to go through creating recipes. I'd recommend using some of the templates that we have either on the SparseZoo or SparseML. So you can look at what a pruning template looks like and what a quantization template looks like. And then you can use those to try and target your model. So biggest recommendation I would make is, as I went through earlier, you know, how we have the all prunable flag, just try that out with global magnitude pruning, see how well that does, and then you can try and fine tune from there. That should get you to probably 90% of the way there in terms of having a performant model, and you might have to fine tune from there, but that would be the recommendation to go through. And we're definitely working on documentation as well to lay this out. So if you'd like to stay up to date on that, feel free to follow us, and we'll be pushing out all these updates as things land. Another statement. So looking at lottery ticket hypotheses, as it takes the paradigm of compression and pruning from during training and after training to before training. So highly optimized models to start with. So this is a good question, question/statement, which is that the lottery ticket did point towards this concept of being able to find a sparse architecture that generalizes as well as the dense architectures, right? So we can get rid of 90% of the weights, 80% of the weights in these models and still have something that's going to generalize just as well as the dense model. This is because sparsity acts as regularization. The lottery ticket took it to another level where it said if you had if you could figure out the initial sparse architecture and additionally a pre-configuration of the weights, then you'll be able to converge to a good solution that's just as accurate as the dense one. The problem with the lottery ticket is that that last part of figuring out the pre-initialization of the weights doesn't actually work out well. You usually have to do what we're doing right now, which is pre-training a model for some time, and then you can start pruning it. And this is where they got to whenever they started trying to apply it to larger data sets other than the kind of toy data sets that they had originally with SciFar and things like that. Once you start looking at these more complex data sets like ImageNet and others, the lottery ticket doesn't hold up as well, and actually doesn't get to as high of sparsity as the pathways that we were talking over today.
Yeah, I think this was connected to an earlier question on like, is sparse transfer learning related to the lottery ticket hypothesis? So.
Oh, gotcha. Yeah, that makes sense then. But yeah, very related. It's just a slight difference in that we have a fully trained model rather than trying to start from a random model with a sparse architecture. And then another question, can there be multiple sparse models with the same performance following the lottery ticket hypothesis? So I'm not sure on performance if this means for inference performance or training performance, but I can kind of answer from both sides. In terms of, well, there might be a lot of complexity to that question depending on how it was worded. But if you look at, can there be multiple sparse models or multiple kind of sparse architectures within a model? This is an active pathway that a lot of people are researching right now. We've put a little bit towards it, but I think it's, it's probably 2 years out or at least a few years out in terms of figuring out how well you can end up with kind of a single model that might have multiple sparse pathways depending on the task or things like that, trying to ultimately get to a model that turning multi-models into a single model that can work across tasks or across modals. Towards the other question, kind of looking at inference performance, there can be a lot that actually happens there, which is something we've looked at, which is that you can actually run multiple sparse models in parallel. That'll be cheaper than a larger big model and actually just use those as an ensemble that can be more accurate than the big model. So you can create, 3 different versions of 3 different optimized versions of a model all optimized to 80% sparsity and quantized, and those will run faster than just the individual model that's not optimized. But now you get 3 different opinions for the ensemble versus just the one. So this can help out, especially whenever you're looking at explainability and things like that. So there's a lot of interesting research going on that right now as well, actually. Another question that came in: what's the best way to go for text classification from my personal experience? In general, I would definitely recommend, I mean, the biggest thing is just making sure that you have a data set that can work with an NLP model first, right? So try and get the smallest model you can, to BERT or something like that. After you've kind of created your text classification data set, you will need at least a few hundred samples labeled. Generally, as more data that you can add, if you can get to a few thousand or something like that, the better you'll end up. But NLP is a little bit harder to get data for. There's a lot of very, very small data sets in NLP that it still does that BERT and other models still do decently on performance. But the first thing is to get that data set defined and make sure you have enough samples there. I'd recommend a few hundred up to a few thousand would work well, depending on the exact data distribution and things like that. After that, try and get just a dense model to converge on it. The smallest model you can, like the BERT or something like that. Make sure that model can converge and that you get good accuracy. And after that, I definitely recommend trying to use one of our sparse models to be able to get more performance on top of it. So you want to prove out that the model is just generally trainable, and then you can use that model as a teacher for the sparse model, so you can create a really fast optimized version once you're ready to go to production. And then another thing, just for clarification, do you support training aware quantization optimizations? How is it done? Because you only presented optimization for trained models. So these are all, everything we're doing here is training aware. You can do one shot with the recipes as well. I didn't go through that, but it is on our README for SparseML if you want to do one shot. But then talking through training aware a little bit more, I think this might be the question on if you can start pruning initially as you're training rather than starting from an already converged model. So we have a little bit of research on that. We actually have ACDC, which is a new algorithm that does that, implemented. If you're interested, definitely dive into that paper. It's alternating compressing, decompressing. It came out of our research scientist Dan Alistar's lab, and it does actually start from a random initialized model, and then over the course of a normal training process, does pruning through that. We don't have support currently for for other techniques like RigL or others like that. ACDC, at least when the paper came out, which was a few months back, was beating RigL and these more what would be considered complicated reintroduction techniques. It's something that we, if you're interested in, if you're interested in trying to add support for, definitely would be open to that. It just hasn't been on our pipeline to try and get RigL and things like that in yet. But we do have support across the pruning algorithms for ACDC, Wood-Fisher, movement pruning, global magnitude, and magnitude pruning. All of these, except for ACDC, working best once you're using it after a converged model. So after you've trained the model, and then you can go to optimization. So yeah, great question. Another question coming in: do you think pruning with regularization will more often get stuck in the local minima of sparsity? Because once weights are pruned, there's usually no way to revive them. So this is actually a really, really good question. There's a lot of research around this. Kind of builds off of the previous thing, where a lot of the techniques we're doing some type of weight reintroduction to try and avoid this, or trying to make sure that we're selecting the best weights possible. So whenever you compare RigL, what RigL is doing is it is pruning, and then it's looking at the magnitude of the gradients of the weights that have been pruned away to figure out which ones to reintroduce back. And it's just essentially alternating across that. So it's, bringing fluctuating, I forgot the exact number, but you can think of it as like 2 to 5% of the weights. It's essentially just continuously reintroducing those so that it can try and get away from this potential issue. There are other ways to get around it though. Wood-Fisher, for example, does really well at just pruning away, and it actually outperforms RigL in this use case without reintroduction. And this is just because it's selecting the right weights, so that you do end up with the correct pathway according to the loss function, so you don't get stuck in kind of this local minima. The other thing that helps out a lot for this is just training for longer. Honestly, as you train for longer for all of these pruning techniques, they pretty much all converge to the same solution. There are, like for RigL, whenever the paper originally came out, they were doing like 5x the original training epochs and things like that. ACDC has something that does the same along those lines. But but this is ultimately just to try and get like the last 0.5% or 1% accuracy. You can get to about 98% of the way there with a very short pruning schedule and work very well. But yeah, great question. And then another question is, how long does your pruning quantization fine tuning take as compared to normal fine tuning time? Yeah, so it differs depending on which route you're going. For sparse transfer is generally right around, or a little bit, it's within 1x to 1.5x the original training time that it took to transfer the model. So for BERT, for example, usually we'll do 5 epochs for the dense baseline to make sure it's converged. We'll do 8 epochs for a sparse version, and then you can get by with about 3 epochs of quantization on top of that. So so you make that work pretty well. And YOLO is around the same. It's about 1x, about the exact same training time for transfer. Whenever we look at pruning downstream, though, this is generally going to be some percent of whatever the original training pathway was, at least on computer vision on large data sets. You can end up with, if you're training for 90 epochs on ImageNet, for example, we'd expect to be able to prune in the range of 40 to 60 epochs. For BERT, whenever we're pruning while fine tuning, though, rather than pruning on the upstream, so we're pruning after we've transferred, this can take longer. And this is why we generally recommend to go sparse transfer. For BERT fine tuning, this can take anywhere from, looking at that original 5 epochs, anywhere from 10 epochs to 30 epochs, depending on the implementation and the hyperparameters to get to that 99% accuracy. And then an additional question on top of that was, are you doing hyperparameter tuning for your parameters or just one pass? Would running a hyperparameter optimizer on top of your package help? So generally what we're doing is setting up kind of a manual grid search across a lot of these to do hyperparameter tuning and looking at hyperparameter tuning across a lot of different data sets at once to make sure that the hyperparameters that we're finding generalize very well. So we, within a data set, we try to do limited hyperparameter tuning just to make sure that what we're pushing out will generalize for whatever data set people are using external from us. But within that, we do have a system of a grid search across that. We have potentially talked about getting a hyperparameter optimizer like the one from Weights and Biases and a few others actually into the package. But yeah, this definitely would help on convergence. And the main thing is just making sure that, again, you're evaluating across multiple data sets so that it can generalize, so that these hyperparameters can generalize for a lot of different data sets versus just the singular data set. That, at least from our side, because we want to push out models that will generalize for everyone. But if you're just looking at one data set, running a hyperparameter optimizer over top of it will definitely help, and will make the process converge quite a bit faster. And then another question coming in: how do you deal with unbalanced data with document classification? So this is something that we're actively looking into. Actually just trying to give an example for those pipelines and make sure that they work. Obviously, anytime we have imbalanced data going through anything, then generally we'll look at either adjusting the sampling that we're doing or adjusting the weight updates based on it. So it'd be pretty similar to what's out in the research papers as is right now. But this is something that we need to explore a little bit more just to make sure that there's nothing tricky that's popping up. So stay tuned for that. That's something that we're working on over the next couple of weeks to try and get an example document classification pipeline working. And we'll definitely be sure to make sure that one of the data sets that we evaluate on has a pretty big class imbalance within it. And an additional question on top of that was, what are the models that take? Let me see. Not sure if I'm getting what this question was supposed to be. Michael, do you know what this one is supposed to be, the second bullet point?
I'm pretty sure it's just talking about specific like data. Like we've had some
Oh,
about, like
for
tabular
punctuation. Okay,
processing, punctuations, case on case, I assume.
gotcha. Okay, yeah. Thank you. So yeah, so right now in terms of the models that we pushed up, we have an uncased version of text that's just going through the standard BERT tokenizer through Hugging Face. We also have a case version that we're currently pushing up of BERT that we'll start taking into case consideration. But generally, all of these are going about kind of just a standard tokenization of stripping out most of the punctuation. And being able to work with that, obviously periods and stuff like that, stay in, at least to get into sentence tags and things like that. It's definitely a good question in terms of, you know, how the tokenization can affect the training process. But the main thing that I'd call out here is that we wouldn't expect it to converge any differently than whatever your dense, your general dense use case is doing. So for example, if you take your dense use case and you change the tokenization around a little bit to account for this, then the sparse should be able to match that as well. What we found is that creating these sparse models actually generalize very well because again, sparsity acts as a regularization here. So it matches towards that dense model very closely. And then another question on, do you know if anyone has tried methods in topology to find out what to prune? This is an interesting question that actually I do not know if there's been any research backing on that. I'll definitely have to look into it because it's an interesting concept, but I do not know off the top of my head if anybody's tried to go through topology before. I haven't seen any state-of-the-art papers that do, I guess would be the main answer there. All right, great. Well, we are these are all really good questions. Thank you for everyone for joining in and staying on and asking all of these. Had a lot of really good questions that came in. As Sasha said, we'll be sharing out the video afterwards. And yeah, definitely stop by. Feel free to follow us, to star us, and to join the community.